This is the video for section 8.2 notes, slides 9 through 11. All right, so in section 8.2, we are talking about volume. All right, volume is when we are going to take a two-dimensional region and we're going to revolve it around an axis to create a three-dimensional object. All right, so let's read this. It says, revolve the region enclosed by the graphs of y equals the square root of 16 minus x squared and y equals 0 on the interval -4 to 4 around the x-axis. All right, so first of all, y equals the square root of 16 minus x squared. That is the top half of a circle of radius 4, which I have drawn here, right? So it's centered at 0, 0, goes from -4 to 4. All right, now what we are wishing to do is to take this region here and revolve it around the x-axis. So this can actually be pretty difficult to visualize. All right, I'm going to use a computer graphics tool to help us visualize. All right, so we have this this region here. It's a two-dimensional region. All right, so now this is graphed in a three-dimensional setting, right? So you can see here's my two-dimensional region, and we're going to take and revolve it around the x-axis. So you can see this little spinner here that shows what we are going to be revolving around. All right, so as I move this thing, you're going to see a three-dimensional solid that is actually created, right? But let me go back a little here. Let's turn it more so that as I move the slider, you can see the three-dimensional solid being created, right? So now what do we actually have? Well, we have a sphere, right? This is a sphere, right? And so now let me undo what I did here. So you can see as I undo it, we can see very clearly that this would be a sphere that's created, right? All right, so this is the object that we're creating it, and that's how we create the object. All right, now it's not really important that you can visualize it or draw it or whatever, but it is helpful to understanding why we're going to be calculating it the way that we are. All right, so now what we want to imagine is, let's go back to our picture here. All right, and let's say that on our picture we draw one of our dx rectangles. Okay, so I draw my dx rectangle. So now what we're going to do is, let's just imagine that this dx is attached to the x-axis, and then we spin the dx around the axis. All right, and so the question is what shape have we created when we spin that around? All right, and so now I'm going to go back over here, and I'm going to show you a different website here. All right, so let's say that we take our dx and we spin it around the axis. What have we created? Okay, we've created what we call a disk. All right, and so this disk, all right, I'm going to kind of tilt it. You can see is just it's technically a two-dimensional object, right? And so what shape is it? Well, the shape is a circle, right? So that is the area of a cross section, right? So if we were to take and cut the sphere, right, we would get a circle, right? So we get a circle. Now, what is the area of a cross section? Well, the area of a circle, very simple, is pi times the radius squared. All right, so now we want to make sure that we're not confusing the radius as being 4. All right, 4 is the radius of this semicircle, right, that created the sphere, and 4 is the radius of the sphere, but it's not a radius of the cross section necessarily. So let's go back over here. So what is the radius of this particular disk that I have created? Well, if you look at it, it's like 3 something, right? You see the height of that is like 3 something, but then as I move the disk, let's see, oh no, I do it over here, right? So as I move the disk, now you can see the size of that thing is actually changing, right? So each one of these disks has its own unique radius, right? And so r is actually a variable. All right. Now, let's say that I put all of the disks on at the same time, right? If I do that, now we can see that we've got this sphere here, right? All these unique disks. All right. Now, what we want to do is we want to think, okay, well, all of these disks here technically are, there's like, I don't know how many of them there are here, 18 of them, right? So as I can, I can add more and more and more, and you're going to see that this is going to get more and more smooth, looking like a sphere, right? But if I do less and less and less, you're going to see, well, this isn't really a sphere. And so the idea is if we can make the disks thinner and thinner and thinner and thinner, right? And then eventually we make them infinitely thin, then we're going to have what is a sphere. Okay? And so what we want to do is, let's, make it a lower number, right? And so we want to imagine, okay, well, if the area of the two-dimensional disk is pi r squared, what is its volume now when we apply a thickness to it? All right, so let's go back here. So now, instead of just having a two-dimensional disk here, now it has a thickness, right? And the thickness is dx, right? So we've got this thickness here. Now, it's like a coin or a disc or something like that. But technically, if you draw it kind of on its side, right? We look at it, it's actually a cylinder, isn't it? So how do we find the area of a cylinder or volume of a cylinder? We take the area of the base and multiply by its height or its thickness, which is actually dx. So we turn a cross section, instead of just being a two-dimensional thing, into a disk, which is now has a thickness, and so it has a volume. So what is the volume of each one of these disks? Well, it would be pi times the radius squared, but then times the thickness, which we're taking as dx. Okay, now remember, dx represents the infinitely thin thickness of that rectangle, which is now the disk. All right, and so then what do we do? Well, what we're going to do is we're going to go back here. We're going to say, okay, however many disks we have, we're going to add up the volume of each of these disks, right? And then together that creates the volume of the sphere or of the object, right? But now, let's say, okay, instead of like right here, I have 13 disks, right? Let's say I went up to 26, well, 37. All of these are just going to be estimates of the volume, right? Until n gets infinitely large, like we talked about before. And if n gets infinitely large, now we no longer have a finite number of disks, so we can't do a finite summation, and so then we have to bring it to the definite integral. All right, and so how do we find the volume by rotation using the disk method? Well, we're going to take pi times the radius squared with respect to x, right? So remember, this is like pi times the radius squared, right, multiplied by the thickness. All right, so now we need to realize this r squared of x. This is not r squared times x. This is r of x quantity squared, right? This is some radius as a function of x. So remember, if you go back here, each one of these disks, right, if I move the disks around, are varying in size. So how do they vary in size? Well, remember, they are dependent on the height of the function at that particular point, right? So if we look at where this is, then the radius of that disk is based upon the height of the function, right? And then let's say we move over here, the radius of this disk is dependent on the height of the function, right? And so if we go back over here, all right, r of x represents the individual radius of any disk, all right? And so we'll talk a little bit more about that in a moment, all right? So now, the cut that we're using, dx or dy, is always perpendicular to what we're revolving around. So for our particular problem, right, we were going from -4 to 4, right, and we were revolving around the x-axis, and so we're using a dx cut because that is perpendicular to the x-axis. All right, but if we were going around, let's say, the y-axis, then we would be using a dy cut because that is perpendicular to the y-axis. Okay? All right, so now, the pi, I always put in front of the integral because it's a constant, right? And so we don't need to have that inside of the integral. All right, so now let's go a little bit further. All right, so I want to find the volume of the sphere that would be created when we revolve that region around the x-axis. All right, so we're going to start off with pi times the integral of the radius squared with respect to x. All right, so now, radius, what is that? All right, so the radius is very simple. It's going to be the height of the dx or dy rectangle, right? So how do we find the height of the dx or dy? Just like in section 8.1, we took the upper boundary minus the lower boundary, right? Or like we said in 8.1, we said f of x minus g of x, all right? All right, so now, if we look at this, what is the upper boundary of the dx? It's the square root of 16 minus x squared, minus the lower boundary. What's the lower boundary? Well, that's y equals 0, right? All right, and if we're using a dx, remember, we have to have our equations in y equals form. Y equals square root of 16 minus x squared, and y equals 0. All right, now, this region goes from -4 to +4, and so we're going to integrate from -4 to +4. right? So that is how we will find the volume of the sphere that is created by revolving the square root of 16 minus x squared around the x-axis. All right, so now we should be able to carry out this calculation. So let's go ahead and do that. All right, so carry out the calculation. I'm going to simplify first because it's going to make the integral doable. All right, so subtracting 0, well, we don't need to do that. But then square root of 16 minus x squared, we just get 16 minus x squared, right? And then with respect to x. So now we integrate, and I put the pi in front. All right, 16x minus x cubed over 3, right? And then we're going to evaluate from -4 to 4. All right, so relatively simple. I know the numbers here turn out to be slightly annoying, but that's fine. All right, so I've got pi times the whole thing. All right, so I've got 16 times 4 minus 4 cubed over 3, right? All of that minus 16 times -4 minus -4 cubed over 3. All right, and the pi is multiplied by everything. All right, so now I have pi times, all right, so 16 times 4 is 64. Minus 4 cubed is 64 thirds. Minus, but then I've got -64, so it becomes plus 64. And then I have a minus, a negative, but then a negative cube. So there's 5 negatives there, so it remains negative 64 thirds. Right? All right, so now, all right, I just want to simplify a little bit more, and I've got the pi in front. Don't forget about that. So I've got pi, and I've got 64 and 64, which is 128 minus 128 thirds. All right, and so I've got pi times 128 times 3, right? So I'd multiply by 3 over 3, and so 3 times 128 is 384 thirds minus 128 thirds, and so I get 256 thirds pi. All right, and so that would be the volume of the sphere created. All right, now what I like to do is also we should double check, right? We actually already knew how to find the volume of a sphere, didn't we? The volume of a sphere is given by 4/3 pi times the radius cubed, right? And so what is the radius of this sphere that's created? It's 4. So 4/3 times pi times the radius of 4 cubed, and so we get 4/3 times 64 pi. And 4 times 64 is 256. So we get 256 pi over 3, right? Which is what we already got, all right? Which is nice. Okay, now don't ask the question, well, why are we doing all this work then? Well, the reason that we're doing all this is twofold. Number one, what we just did verifies the formula that you've been taught, right? This is like the proof that that works. Right? But then also, we're going to have shapes that are not regular, shapes that we do not understand how to find the volume of in geometry. So let's go on to slide number 11, and we'll have an example of that. All right, so slide 11. All right, so it says, find the volume of the solid generated when the region bounded by y equals root x, y equals 0, and x equals 1 is revolved about the x-axis. All right, so you need to be able to come up with this graph. Y equals root x, obviously, top half of a sideways parabola. Y equals 0, horizontal line, the x-axis. X equals 1, vertical line. All right, now we're taking this region right here, and we are revolving it about the x-axis. So if we're revolving about the x-axis, that means we're using a dx, because dx is perpendicular to the x-axis. All right, so then I'm going to start off with pi times the integral of parentheses squared with respect to x. That's how I start every single problem. All right, so now, what is the radius? Remember, the radius is the height of the dx, the upper boundary minus the lower boundary. All right, so what is the upper boundary? The upper boundary is the root x. So root x minus the lower boundary, which is 0. All right, so now we're integrating from what to what? Well, how far to the left does this region go? Remember, we're looking for the x value, which is 0, right? This point is 0, 0. Right, and how far to the right does this go? Well, this point is 1, 1, right? But this point is 1, 0. So what are we using? Well, remember, we're going from left to right. So the right-hand value is the x value, which is 1. All right, so this would be the volume of the object that's created. Now, some people say, well, okay, well, what is the object? All right, so let's say that we take this and we revolve it around, right? If we revolved another one around and another one around and another one and another one and another one, another one, we're going to get an object that kind of resembles this, right? Now, you don't have to be able to describe what it looks like. You don't have to be able to draw a picture of what it looks like. it's just sometimes nice to kind of have an understanding of what it kind of looks like. All right, so anyway, let's continue the integral. All right, so I've got pi times the integral from 0 to 1. All right, if I have the square root of x minus 0, that's just root x, and I'm squaring it, that's just x. So this is actually a really easy integral to carry out. I get pi times x squared over 2 evaluated from 0 to 1, and so pi times 1 squared over 2 minus pi times 0 squared over 2. So we get pi over 2. So pi over 2, or approximately 1.57, would be the volume of this solid.